We have been going on and on about uncertainties. So what do models actually do to deal with some of these? The so-called biases, where there are systematic differences between models and observations. For example, here is the rain in millimeters per day from the original model output. It's got, let's say, maximum here of over 35 millimeters per day and over 20 millimeters per day here. And you look at this particular time period, the bias correction is done to reduce the amount of rainfall here from over 20 to under 20, and it's done by basically using observations. When you have good observations, you can look at the distribution of rainfall, let's say, because rainfall is a very episodic positive quantity. There is never a negative rainfall. So you can create distributions and match model distribution to observational distributions with some computations that are meant to remove these sorts of biases. And you then look at the bias corrected model precipitation with the observed precipitation. You started out here and you ended up down here, so you are improving the relation between observed precipitation and modeled precipitation. So you are not always going for absolute amounts to be correct. You are trying to sometimes produce probabilistic distribution. For example, this is done for let's say predicting rainfall for use in irrigation water application. I'm talking about something specific that I am involved in with some colleagues here at the Indian Institute of Technology in Bombay. There you take the prediction of a model and you look at its distribution, you look at observed distribution, and you produce probabilities of rainfall that are realistic compared to observations. So this is a very simple example. There are very sophisticated examples, and this figure here, looking at many models involved in IPCC scenarios, is looking at what difficulties you can still face in terms of trying to correct biases. So this is showing for Amazonia rainfall regimes from observations and simulations. So you have on the x-axis here maximum climatological water deficit. So you can see 0 is over here and deficit increases this way. So obviously you go from rainforest where water deficit is very low into savannas where rain deficit is very high. So it's a clear shift in vegetation type. So you look at annual precipitation in millimeters and you want to see what the models are projecting. The observed is over here, and these various models, without worrying which one is which, you can see that they're all pointing this way of in decreasing precipitation and increasing water deficit, which means they're heading towards a savanna. They're trying to shift the Amazonia towards savanna under certain scenarios. Okay, and when you do bias correction, you are bringing all the models to this baseline based on observation, and some models are now pointing in the right direction, but most models are still pointing in the wrong direction. One of them is severely heading into a regime of savanna versus seasonal forests and rainforests. So bias correction is not a silver bullet, it's not a panacea, it can still have problems. So one must then understand why this model is going crazy here and why these are all pointing in different directions. It could be a combination of thermodynamic uncertainties in models, which means the moisture dynamics, cloud feedbacks, etc., and dynamic responses to increased greenhouse gases like the circulation itself. In general, as we saw before, circulation doesn't change as severely as the moisture dynamics, so one has to understand those combinations. And of course there are the details in the way the vegetation itself is represented and how water deficits are computed and so on. Okay. The other uncertainty that I already mentioned, emission uncertainty of a single model versus model uncertainty, are important to consider as well. Okay, so we are looking here at petagram carbon per year. From scenarios we produced based on concentrations. So the model, integrated assessment model, went after socioeconomic scenarios, energy, and other combinations of technology, population, etc., to produce these radiative forcings corresponding to ppm, atmospheric concentration. Then the Earth system models are going to take that forcing of RCPs and produce carbon stocks based on all the carbon cycle dynamics. So they are kind of in the same envelope over the historic period, but for future projections, when you look at the integrated assessment models shown in this broken line for each scenario versus the CMIP 5 mean, you can see that the differences can be significant, especially for this scenario. They are much closer to each other here in the RCP 2.5 and 4.5, 2.6 and 4.5 and 6 as well. But the difference is large over here because this is the high emission scenario. So the higher the emission, the concentration, larger seems to be the difference in the carbon cycle and the carbon that remains in the atmosphere reservoir. Okay, so these are not trivial issues. They have to be understood carefully so that the uncertainties are characterized and made understood, so that decision makers can actually know what are the scenarios being provided corresponding to, what do they mean in reality. So for example, if the future plans of afforestation are going to depend on reducing total carbon, right, because you measure carbon uptake by new forests in gigaton carbon per year. So India, for example, promises 2.5 to 3 gigaton carbon source from afforestation by 2030. So that's not a ppm calculation, that's a carbon calculation. So this conversion between concentration and amount of carbon is required, but there is always that carbon cycle in the middle with all its components in the ocean, in land, and in the atmosphere that have to be taken care of in terms of the uncertainties.